Okay, good morning everyone. So I am Swaprava and I'll be talking about my research, which is in mechanism design, and this lies at the interface of computer science and economics. And my overall plan for this talk is to give you some samples of my work, which kind of tells you the story about what are the problems which are using the tools, the mathematical tools used both in computer science as well as in economics. So some of the research areas that I want to mention here is definitely voting. So where we have a different preference over alternatives, and collectively we want to pick one or multiple alternatives. That is what is called voting. And we'll see in the later part of the talk how we can quantitatively measure some of the goodness of certain voting rules. So this is a mechanism where you do not use transfers, that is the value that a particular agent gets when a particular candidate is selected. You cannot transfer those utilities. So there is a bunch of literature where you take this collective decision making, but you also have the choice of transferring utilities. So this is the way you transfer utilities across agents is by money, and that's the collective choice with monetary transfers. We'll be talking about that as well. The other application domain, so all these research areas are kind of motivated from certain application domains. So participatory democracy is one important aspect of design of democracy, which is kind of polar opposite to what we are kind of exposed to. So instead of selecting one representative who takes decisions on our behalf, the society directly can decide on whether to build a bridge or build a park or how to divide the collective budget in a certain way. So there are certain kind of interesting problems that we can ask, which is computational in nature. One of the projects that we are currently working on is on peer grading. So this is where to manage large classes, instructors can allow the participants or the students to grade themselves, grade one another. And this helps in two ways. First is that you can now handle a much larger class without having to hire a lot of TAs or instructors. At the same time, you can also take your courses outside in the world and make it really reachable to those places where quality of education is not great. And it works very much for the developing economies. And finally, I also currently working on doing something which is self-enforcing the people to do environmental protection. So imagine that in a large city like Bangalore, there are many people who are taking the rides from one place A to place B. And if instead of taking individual rides, which is actually hurting the environment a lot, we can pull them together in one car and let them go in the same destination, but it will impact the environment a lot less. Now the question is whether people will self-enforcingly take that decision by appropriately choosing those prices. We can actually ensure that people can take those rides, which are shared rides instead of solo rides. Now these colors essentially represent that what kind of analytical toolbox we use, what kind of analysis techniques we use. Game theory and mechanism design is kind of common for all these problems, but in many topics we use nonlinear optimization, rail analysis, approximation algorithms, and several other analysis techniques. So let me just focus for this the next 10 minutes on the first two problems, that is voting and collective choice with monetary transfers, starting with the second one. So the mechanism design with incomplete information has the common setup where you have a bunch of alternatives to pick from. Suppose there are m alternatives, and there are individuals who have preferences or valuations. So what is the difference? So by preferences, we typically mean that they do not associate a real number to each of these alternatives. You can either rank them or you can ask pairwise questions, but there is no way to know with what intensity they like each of these alternatives. On the other hand, valuations say that you have a particular value for a particular alternative. So suppose I get a picture or I purchase an item, I exactly know how much dollars or Indian rupees we value that object. So we will talk about both of these, the ordinal ones and the cardinal ones. Classically, in mechanism design, the two standard models that are used, one is without monetary compensation, without monetary transfers, like the voting, matching, where you match students to universities. There's no monetary transaction that is happening there. But also, on the other hand, you have this auction thing where you have monetary transfer. You can actually take a decision and also ask people to pay a certain amount of money in this kind of models. Now, what are the benchmark questions or results that are available in these domains? So in the voting model, suppose we assume that there are at least 3 alternatives. This is kind of quite common in all the results. You have 3 alternatives. 2 alternatives have, those are too easy to design mechanisms. And suppose all preferences, all strict preferences are admissible. So if we have m alternatives, all m factorial ranking of those things are admissible. People may have those kind of preferences. The question that we are going to ask in this voting model, that what kind of social choice functions, so social choice function is a function which takes as input the preferences of all the people sitting in this room and selects one alternative, one candidate, let's say. So those kind of functions are strategy proof, which means that none of us can change our preference and be better off. So if I reveal my true preference, candidate A wins, and if I change my preference, some other candidate, let's say B wins, which is actually above A in my case, in my own preference. That will not happen. That is the guarantee that we want to give to design these social choice functions. And to give an example, suppose we pick one constant alternative. So no matter whatever people report, I always pick one particular alternative, build a bridge or something. This is clearly strategy proof. Nobody can change the outcome in any way. Therefore, it's weakly truthful. You can also think of another mechanism, which is like I select one individual and always pick his or her top choice. So that means he or she is the dictator, and whatever she likes the most is going to be the social outcome. This is also truthful because that particular individual has no reason to manipulate, because her most favorite candidate is winning, and for others it does not matter. So they are also weakly truthful. Now the answer to this question was answered in 73-75 by Gibbard and Satterthwaite, which says that if you look at all possible social choice functions that are strategy proof, using that all preferences are admissible, they can be only dictatorial ones. So all the voting rules that we use are essentially can be manipulated. All plurality, what we use in India, some other things which we use for other purposes, all can be manipulated. Now the question that we can ask in the corresponding domain of mechanisms with money, and the mechanism with money is given by the quasi-linear model. That is, you have a value minus the payment. That is essentially your net payoff. We can ask the same question: what are the social choice functions which are strategy proof? And this was answered by Roberts way back in 1979, and the answer in that case was affine maximizers. So let us get to what affine maximizers are. So imagine that each of the individuals are given a particular weight, wi's, and we take the weighted sum of all this of all the agents. So wi times vi summed over is a weighted sum, and then translate that with a function called kappa. So this is an affine sum of these numbers, and pick the alternative that maximizes this affine sum, and thereby the name affine maximizer. What Roberts has shown, so you can see that many of the mechanisms that we just talked about are actually special cases of affine maximizers. What Roberts said is that if your valuation space is unrestricted, and we'll get into a minute what we mean by unrestricted, then the only social choice function, very similar to what we discussed about the Gibbard-Sadov weight, that all possible social choice function must come from this class of affine maximizers. The wi's and kappas may differ, but this is the only thing that you can implement in a truthful manner. Now, what is the limitation of Roberts' theorem? It does not hold on certain domains. For instance, in the case of selfish valuation. So suppose we are in a domain where people only value what is the resource share that he or she is getting from the different resources. So the rows and columns you can just change with the service providers and different frequency bands, 4G, 3G, etc. And Bob only cares about the resource share that he is getting. So this is a matrix which shows the resource share. And if that is the case, and Bob does not care about what Alice or Carol is getting, then Bob's valuation for these two alternatives, X and Y, where other people's valuations, resource shares have changed, should remain the same. And this is not covered under Roberts. It requires that the value difference between two alternatives, X and Y, should be arbitrary. It can take any real number, but in the domain of selfish valuations, it will always be 0. So in some sense, the Roberts theorem, the proof of Roberts, does not go through, so it will not immediately give you the result that what will be the, so we can ask in this domain, what is the social choice function that is a strategy proof that will not be given by Roberts. However, we can show that the affine maximizer result holds with one additional assumption, and a different proof technique. And that is exactly what we did. So this is my work with Arnavas N. And we have shown that this property of allocation non-bossiness, which I'll be happy to talk about offline. I don't have time to discuss about that here. And there is a certain richness requirement needed for this allocation space. Then you can get back this affine maximizer result, very similar to Roberts. The proof technique uses the fact that the allocation domain is continuous. This, what we show is that this Roberts kind of argument works everywhere except those points where the components are not similar. So if there is at least one component similar, then we cannot use Roberts. For everything except those points, and we show that those points essentially form a measure 0 space, you can use the arguments of Roberts and using a continuity argument, and that's why we need the richness of this A and also this additional requirement that we can follow the same argument by continuity to hold even those points which has two components which are similar. So this is part A. I mean, I'll be happy to talk about this offline. What are the tools required? So you can clearly see that real analysis forms a significant part in analyzing this part. The second part is where we talk about the preferences and domains. So let's say the same preferences, so P1 to Pn are the preferences, the rankings of different alternatives for different agents. And if we restrict these preferences into a certain domain, for instance, we can restrict it to a single peak preferential domain. So this was introduced by Black. Let's not get into the formal definition. Let me explain this with a figure. So suppose there exists an intrinsic ordering of all the alternatives. So CBA is left to right for all of us. So think about this as the temperature of the room. For everyone, the temperature scale, 25 is more than 24 for all of us. And we all have a sweet spot, a temperature that we like the most. Anything hotter or colder will be worse for us. And that is exactly what is represented by a single peak preference. So if my most favorite temperature is B, then I may prefer C more than A or A more than C, but there won't be any case where I prefer C more and then A and then followed by B. That won't happen. So that is exactly what it is called a single peak. There is only one peak. So we are actually removing some of the preferences out of 6 factorial. If you have 3 alternatives, then you will have 3 factorial, which is 6. 2 of them are actually taken away. Now, why do we care about the single peakness? Because it provides a number of nice properties. I'll just take 2 more minutes. Single pickness provides a number of nice properties, including non-manipulability. The thing that we just discussed about, that all the voting rules can be potentially manipulated, but in the single pick domain, if agents' preferences are well behaved in some sense, we can bring back this non-manipulability by something which is not dictatorial. So let me just skip over why we need to test, but think of this in a way that we have both advantages in terms of what kind of mechanisms we can design, and also we have computational advantages. So if we could somehow know that the people of this room has a single pick preference on arbitrary alternatives, then that will be very essential for us so that we can design mechanisms and we can compute it easily. So the goal is to figure out, given a bunch of preferences of all of us, whether this is coming from a single pick preference domain or not. And the current state-of-the-art algorithms use what is known as recognition algorithms. You are given a particular profile, and you are asking whether this profile is coming from that particular domain D or not. Now, there are mechanisms which gives polynomial time algorithms for this, but somehow the polynomial includes this number of votes. So in some sense, you are going to scan over everyone's preference and then decide whether this is going to be single picked or not. So this is one disadvantage of this kind of an approach. In particular, the pre-election polls or surveys only sample a partial population which does not scale with the population. So if you have certain amount of resource, you cannot really ask everyone to fill in a survey. The second important point is that none of these none of these special domains, so none of our preferences match exactly with a specific domain. It could be very close to a single pick domain, but it might not be perfectly a domain. So the answers from this kind of algorithms will give you a no, which is not very useful because we do not know how far we are actually from a single pick domain. Maybe 90% of the population, if we just delete 10%, is a single picked preference, but that 10% is something else. So our approach is what we call as sampling-based approach. So we want to distinguish between two different generation models. So one generation model, which is coming from here, is if we have m alternatives, we have m factorial possible orderings. Uniformly at random, you can generate those n preferences. Or with 1 minus epsilon v fraction of those preferences are coming from a single pick preference, that specific domain, and the rest is coming uniformly at random from any possible preferences over those m alternatives. So now our objective is to classify by sampling a subset of these profiles to predict whether this is coming from profile 1 or profile 2. And the answers that we have is that you only need to sample a constant number of voting preferences or votes. We only need to sample a constant number of votes in order to decide whether this is coming from that profile 1 or it is completely random, that is of profile 2. So there are several other results which are also kind of talks about this distinction between different generation models, but I'll be happy to talk about those offline. So what is the advantage? So we can actually say that this is not exactly a single pick, but it is very close to the single pick domain. But we are also giving this answer by sampling a constant number of things. And this is a probabilistic answer, that is, by sampling, I'll be able to tell you that this is coming from profile 1 or profile 2 with probability at least 1 minus delta. And as you want to decrease delta, so more precise information you want, the more you need to sample. That's essentially the takeaway point. Okay, so let's stop at that point. So this essentially uses the concentration bounds, which are asymptotic in n, to find all these results. I'll be happy to take questions. Okay.